Hello. Okay. Excuse me. So good morning, everyone. I hope I'm audible. Yes. Okay. Yes. So good evening, everyone. Myself, Varad Dav. I am a PMRF fellow and also a doctoral student at the Department of Chemical Engineering, IIT Kanpur. So today we are entering into the third week of the NPTEL course on thermodynamics of fluid phase equilibrium. So in this lecture, what we are going to see are the third week of some practice problem for the third week of the course, which is thermodynamics of fluid phase equilibrium. I will just wait for 5 minutes for people to join, and then we will start. And in the meantime, if anybody has any questions from the previous uh, weeks, they can ask. Uh, Otherwise, we'll go to the this week's content, and we'll wait for 5 minutes for the people to join. Okay. So we'll wait for 3 minutes more for people to join, and then we'll start. Okay, so we'll start in just 2 minutes. Okay, so we'll start. Um, so once again, like I said, I welcome you to this third week of uh, NPTEL course on the thermodynamics of fluid phase equilibria, and myself, Varad Dav. I am a PhD scholar and a PMRF fellow at the Department of Chemical Engineering, IIT Kanpur, and this and what we are going to cover in this video is the third week of the NPTEL course. Some problem solving, some sample problem solving, which will be able to help you in your assignment solving. And we are going to solve some sample problems for this third week of this NPTEL course. Okay, so we'll start. So the first question I'm giving is, so let us read the question. So saturated liquid. So from this, what you understand, saturated liquid means it's completely liquid. Okay, complete liquid. Okay, so what we have is, let me just increase the font size. Okay, okay. So what we have is, okay, what we have is saturated liquid. That means it's that is its quality is 1. Q is equal to 1. That means complete liquid. Complete liquid. Okay, and it is at 100 and it is at 1500 kilopascal and 500 Kelvin, and it's a saturated liquid with an enthalpy of 750 kilojoule per kg. So we are given HI, that is H initial, or which is nothing but H liquid, enthalpy of pure liquid at this P1, which is equals to 1500 kPa, and sorry, and temperature is equal to 500 Kelvin. Okay, and is throttle. So remember, what we have used is throttle. This the pure liquid is throttled to a liquid vapor mixture. Okay, so you can understand like this. So like for example, okay, what we have is throttling. Okay, so here it is pure liquid, and either vapor plus liquid. Okay, and here H1 is given as this H1, this is equal to 750, right? 750 kilojoule per kg. Here it is given 750 kilojoule, and this liquid is throttled at 150 kilopascal and 300 Kelvin. So here, so the conditions is 150 kPa and 300 Kelvin, and the thing is it is throttled. So let me use a different color for this. It is throttled. Okay. At the enthalpy of the saturated liquid. So here enthalpy of pure liquid is given as 500 kilojoule per kg, and enthalpy of okay, and enthalpy of vapor is given as HV. HV is given as this value, 1500, okay, 2500 kilojoule per kg. And what we are asked to find is the percentage of the original liquid which vaporizes. That means we have to find the quality, right? Q. And throttle means the enthalpy here. Total enthalpy here is going to remain same as enthalpy at here. Okay. So remember the keyword which is to be remembered here is throttle. That means the enthalpy is going to remain the same. So the way we are going to solve is enthalpy at initial condition is going to remain enthalpy at final condition. But here we have pure liquid. Here we have liquid plus vapor. So enthalpy at pure liquid is given as 750 kilojoule per kg. Okay. Always remember to write the units. Kilojoule per kg. This should be equal to enthalpy of liquid. So HF will be what? Enthalpy of liquid plus 1 minus this quality. That means amount of liquid per total amount. Okay. Multiplied by, or we can like let me just, okay, multiply 1 minus x into Hg of enthalpy of vapor. So G here stands for vapor. So I will just clear it and I will go to this, move on to this. So now this has been given 750. This has been given as 500, and this is given as 2500. Okay. And what we are asked to find this x value. So I hope this is clear. So if anybody would like to try, you just plug in the values and get the answer. In the meanwhile, if I will show you the handwritten. Okay. So here you can see it is very nicely written that H1 initial H is going to remain, is going to be conserved. Why? Because it is throttling process. So H1 is 750. So this is going to, so 750 is equal to HL plus 1 minus x into Hg. Okay. So this is the X is the mole fraction of the liquid. This is also called as quality. Okay. Mole fraction or mass fraction. When we know it is not mole fraction, it is mass fraction. Okay. Uh, because why? Because here it has been mentioned kilojoule per kg. Okay. So that means this is mass fraction. Okay. So now this is mass fraction. And then if you just put in the value, you get that x is equals to 0.85. Okay, but this is what amount of liquid. So what we are asked, we should go again and try to find what is that we have. So 87.5% of the total amount of liquid has been converted, has remained in the liquid, right? But what we are asked is, we are asked percentage of original liquid which is vaporized. Okay, so which is vaporized, so it will be 1 minus x, right? Because this much, like I said, x is the mole fraction of liquid, right? So this is the amount of liquid which is present afterwards, finally, and the amount of vapor will be 1 minus x, right? So amount of vapor is 1 minus x. The fraction of liquid which vaporizes is nothing but 1 minus 0.87, which is 0.125. And when you convert it into more percentage, you get 12.5, right? So anybody has any problem? I hope this is clear to everyone. I'll give you 2 minutes. I hope the question is clear to you. So if anybody has any doubts, concept is clear to everyone. So the correct answer is option C, 12.5%. Okay. Okay. So those students who could who understood the question 1 and move on to the question 2, and those who want to ask, they can ask. Okay. So let me read the question. So at constant T and P, so T here stands for temperature, P stands for pressure. The molar density, remember this is molar density in that uh, mass density. Okay, so that will be, okay, of a binary mixture, okay, is given by rho is equals to 1 plus x2. So x2, where what? X2 is the mole fraction of the component 2. Okay, the partial molar volume of component 1 at infinite dilution. At is what they are asking. So what they are giving is basically what they are giving rho is equals to 1 plus x2. Okay, this is rho total, and this is it. Let's say some mole per meter cube. Okay, because it's a molar density. Okay, and what they want is they want V1 bar. Okay, V1 bar are infinite condition. This is equal to what? So I hope the question is clear to everyone. So I'll give you a couple of minutes to think about the question, and then I'll give a hint. So remember what we have is try to remember the definition of partial molar property. The partial molar property of component 1 in a mixture at x1 equal to 1 is what? Remember, this is dou by dou n1 of total property at constant n2, right? And what we can say, once we get this m1 bar, so we just have to put 1 m1 bar infinity is what? It will be m1 bar at, just put in x1 equal to 0. That one give us m1 infinity. So somehow, if you are able to find the expression for m1 bar, you just whatever expression it comes, you just put x1 equal to 0, then you will get a m1 bar infinity. That is what they are asking. So here m stands for v, volume, and m1 bar depends on mt. Okay, total. And remember, like this will connect with this row. So you have to think in the line of how you can convert row to mt. So here m will stand for v. So how can you convert rho to V? Remember, this is rho T, total molar density. So how can you convert it to total molar volume? If you are able to convert it, then you just have to take the partial derivative with respect to n1 or x1, and then when you put x1 equal to 0 in the expression, you will get the m1 bar infinity, right? This is v1 bar infinity. Okay, so I hope the question is clear to everyone. So I'll give you a couple of minutes for those who want to solve it, and then I will start with my explanation. Okay. In the meantime, I will erase the code. Okay. Okay. So anybody got any answers? So I'll give you first the answer. So the answer is option A, 0.75. Okay. Anybody got it? Nobody got it? I will start with the explanation. Like I said, so here, what we are asked to find is, okay, what we are asked to find is, we are asked to find what is V1 bar infinity. So we'll just do what is V1 bar. So V1 bar infinity. So it will be nothing but V1 bar at x1 is equal to 0, right? Then but what is V1 bar? V1 bar is nothing but dou by dou n1. So here it's a binary mixture, right? So this will be Vt, total molar volume at constant n2, right? And what we are given is rho. Rho is 1 plus x2. Okay. And each unit is kilomole or mole per meter cube, like this. Or matlab, it will be a molar unit divided by volume. So if you just take 1 by rho, so what you will get? 1 by rho is 1 by 1 plus x2, right? And its unit is going to be meter cube per mole, right? So this unit is nothing but total, right? Because this is total density. So it's 1 by its reciprocal will be the total volume. Hence, what we get is okay. So what we get is V total molar volume is nothing but 1 by 1 plus x2, right? And what is going to be V1 bar? So V1 bar is nothing but dou by dou N1 of 1 plus x2 at constant N2, right? So if you convert x2 to mole fraction into number of moles, so it will be 1 by rho N1, 1 by 1 plus N2 by N1 plus N2, which is going to be N1 plus N2 dou by, which is going to be, let me just rewrite it, which is going to be dou by dou N1 of N1 plus N2 divided by N1 plus 2N2 at constant N2. Okay, so if you are able to differentiate it, then you will get V1 bar. So V1 bar is dou by dou N1 of N1 plus N2 divided by N1 plus 2 times N2 at constant N2, right? So once you differentiate this expression, and then you put x1 equal to 0 or n1 is equals to 0, we'll get the expression for v1 infinity, and the value will come out to be 0.75. Okay, so anybody would like to try differentiating this expression? So please, can anybody give me an answer for this? Try to differentiate this expression. Meanwhile, I will clear the board. Okay, so I hope this question is clear to everyone, right? It is just the definition which we are using. So it is very important in this course that you remember the definition. You don't have to remember the formulas. You don't have to mug up the formulas. Only if you are able to remember the basic definitions and their physical significance, then you will be able to solve most of the question. Okay. Okay. So let me share how this differentiation is done. Okay. Okay. So here you see rho is 1 by x2. We just take inverse of that. We get the specific volume. We get the total volume. Then here what they have taken. So instead of doing the differentiation the way I have done it, we can use or the form. So that way, the differentiation was very difficult. So instead of converting it to N1 number of moles, you can also keep it in mole fraction. So this is the way how it is done. Okay. So x2, we know it is a binary mixture. So x1 plus x2 is going to be 1. That means x2 is going to be 1 minus x1. So this is what they have replaced here. Then you just do the simple arithmetic, you get this, and then so this is the expression applicable for binary mixtures. Okay, so you can do it the way I have also shown you, that dou by dou n1 of n1 plus n2 divided by n1 plus 2n2 at constant n2. This is nothing but v1 bar. Okay, so you can go this route or you can go this route also. This is the definition of partial molar property, and this expression is specifically for the binary mixture. Okay, the second, I hope you have seen the lecture in which this method is called as a second method, which you can just substitute in this thing and you can find that v1 bar is equals to total. So this is total plus x2 into, so it's partial derivative d by dx1. Okay, so you just put in. So what is v? This is 1 by x2. Okay, that is nothing but 1 by 2 x1 or 1 by 2 minus x1. So let me just, okay, okay, okay. So this is v. So v is what? This one, right? So this is what they have explained. Then x2. So x2 multiplied by d by dx1. This is 1. So x2, this is x2. X2 is nothing but 1 by x1 multiplied by this thing, right? Which is nothing but this. And now you put x1 equal to 0, right? Limit x1 equal to 0, v1 is nothing but v1 infinity, and then you get the answer as 3 by 4. So if you put, it is 3 minus 0 divided by 2 minus 0 square, okay, which is nothing but 3 by 4, right? Which comes up to a 0.7. So both the routes, this route is also correct, whereas and this route is also correct, even though this appears to be mathematically simple, and this appears to be mathematically complicated, but both of these things, both of these will eventually give rise to the same answer. Okay. Anybody has any question? Okay. I hope this is clear to everyone. If anybody has any question, they can ask. Okay. So for those I am who are clear with this question, I will be showing the next question. They can try solving this question, and those who want to see the solution, they can just see it here, right? And if they have any question, they can ask. So I hope this is clear to everyone. I see no questions on the chat or anybody asking. So I will move on to the next question. Okay, let me read the next question. Okay, so what is the residual volume alpha is given by this expression. So they have already given the expression for residual volume. Then find out the relation for dou p dou vt. The result is expressed by empirical correlation given as this. Okay, so you have been given this, and what you want to find is dou p dou vt. Okay, so anybody would like to try it, they can try. I'll give 2 minutes, and then we'll go. I will be showing the solution. Okay. Okay. Try to remember. Okay, this is residual volume. Okay, this is VR. So and so just try to remember the VR has been given as this, right? If you remember this, you can also, this is the ideal volume, ideal gas volume minus the real volume. So that is the definition of VR. VR is okay. So if you can just connect the definition, you remember the definition of VR and then connect it with this and just take the partial derivative of pressure with respect to volume at constant temperature, you will be able to obtain. So this, I'll give you 2 minutes. I hope the question is clear. You can start solving the question. After 2 minutes, I will give the solution. Okay. Anybody got it? I hope the question is clear to everyone. So I'll give the answer. Anybody got it? Anybody would like to guess the answer? So the answer is this, option C, right? No, answer is I think option A. This is the answer. Okay, this is the answer. Anybody got it? So let me start. Okay. Okay. So what we are given? We are given residual volume expression or expression for residual volume, which is alpha, and it is given by RT by p multiply minus v. So what we are asked, do p, do v, t. Okay, so either we can just take away the take the partial derivative, or we can rearrange it. So here, for simplicity of mathematics, we will just rearrange it. So we just take v from here to here. So we get v alpha plus v is equal to RT by p. Okay, where alpha is equal to this thing. And then again, sorry, and then again we rearrange it. Okay, we rearrange it, just take, okay, p we take here, and we just swap it, and alpha by v comes up to be here, p is equals to RT by alpha plus v, and v has been given as this. Okay, this is the residue. Okay. Okay, then we just substitute, because if we take now partial derivative, alpha will come, right? It's like alpha, this term will come, alpha p by alpha vt. Okay, so before doing it, we just plug in the value of alpha, just put in here, and then now we have everything in p, t, and v. Now we can take the partial derivative. Okay, and once you take the partial derivative, so how it will be, p v do p, do vt is nothing but 2 by do v of RT by 2 minus 3 by v square plus v. Okay, this is nothing but RT, because temperature is constant and R is anyway constant, minus into minus 1, or you can just say into dou by dou v of 1 by 2 minus 3 by v square plus v. Okay, this is just a derivative. If you know, or you can just take the derivative, so you can just treat it like 1 by x for x. Then it just depends on how you solve it, but eventually you come out to get this expression. Okay, okay, eventually you reach this expression. Just take the derivative. Okay, this expression you will get. Okay, okay, this has been given, which we are using it here. Okay, and it is just a question of how do you do the differentiation, just a mathematically challenging question. Okay, I hope the question is clear and explanation is also clear. If anybody has any question, they can ask. It's just a simple mathematics. Okay, so those who got it can go move on to the next question, and those who have any questions, they can ask. Who didn't understand how to take derivative, you can just refer back to your class 12 uh, notes on how to take the derivative, and then you will be able to solve this question. Okay. Okay, so I hear no question. So I hope that this question is clear to everyone, and we'll move on to the fourth question, the next question. So the question is expression for fugacity coefficient for the gas obeying the equation of state. So if we are given an equation of state of a gas, and we are asked to find the fugacity coefficient. Okay, so first of all, what is fugacity coefficient? So this is a very easy question. If you can just remember what is the fugacity coefficient and how do we find this expression, it's a straight away question. Just try to remember what is the definition of fugacity coefficient, and then very easily you will be able to find what is this. Okay. Okay, so I'll give you 2 minutes for everybody to solve the question. Okay, and then I will give the answer. Okay. So just remember what is the expression for fugacity coefficient. What is the definition? I'll give you 2 minutes. It's a very straightforward question. You just have to put in, you just have to understand what is fugacity coefficient, then just put it in the formula, this equation of state, and you'll be able to get. Okay, anybody got it? So I'll give you a hint. So the expression which we are going to use is ln f by p is going to be integral p is equal to 0 to p is equal to p z minus 1 by p dp. Okay. So now remember what is this z? Z is nothing but PV by RT. RT or NRT depends on how you are calculating the volume. Okay, and use Z for this thing. You can calculate from here, and then you just plug it the value here, and then you will be able to find. So F by P is nothing but fugacity coefficient, right? Okay, because this is nothing but F by P. This is what we are asked. Okay, just a simple mathematics. Okay, I'll give you 2 minutes to solve it. Anybody got it? Okay, so I'm just going to simplify this expression. PV minus PP is equals to RT. Then divide all the things by RT. PV by RT minus PB by RT is equals to 1. This is what Z. Z minus PB by RT is equals to 1. So Z minus 1 is equals to PB by RT. Okay. So Z minus 1 by P is equals to P by RT. Okay. So ln of F by P is nothing but ln of fugacity coefficient is nothing but integral P is equal to 0 to P is equal to P, and just plug in this value B by RT. Okay, dP. So we assume that this B is not changing with respect to pressure, and anyways R and T is going to remain the constant. This is nothing but B by RT into P from 0 to P. Okay, so ln phi is equals to dP by RT. That means we just take the exponential, so phi is equals to exponential of dP by RT. Okay, this is the answer which we want. So the correct answer is option B. Right? So anybody got it? I hope the explanation is clear to everyone. Okay, we can just start with this. So anybody will, so this is the expression. You just have to remember what is fugacity coefficient and this expression. Okay, and the rest of the things. So ln f by p is equal to z minus 1 by p into dp integral. So just you find z from here, z minus or z for this expression. You just straight away get z minus 1 by p b by t, which you just express, put it in here, do the integration, and you will get the answer. So I hope the question is clear. So, oh, sorry. So, okay. So I have also done the mistake. So remember to, don't do the this mistake. So answer is not this. Answer is this because fugacity coefficient ln. Okay, ln of pi. This is what we are asked. Okay. ln of f by p is nothing but bp by rt. Okay, so let me just, Okay, and then let us go back to the clear. Okay, so okay, so now we are good. We have been given this P into V by RT. PV is equal to RT by PB. We just divide it by RT on the both the sides, and then Z is equals to PV by RT. You just rearrange and you get Z minus 1 is PV by RT, and then we know fugacity coefficient, which is nothing but ln of pi. Okay, okay, and then we get ln of F by P is PV by RT. So I think, and then F by P is nothing but our fugacity coefficient. So if they ask what is fugacity coefficient, you go exponential of PV by RT. And if they are asking what is the ln of pi, then you go the answer is PV by RT. Okay, so depending on the question. So here they have asked. So here what they have asked is ln of pi, right? So here it should not be expression for ln of fugacity coefficient. Is what they have asked. But there is correction. So if they have asked this, then the answer is going to be this. And but if they are asking what is the fugacity coefficient, as per definition, this will be the. Okay. So anybody has any question? Right, this is the thing. So nobody has any question. So if anybody has any question, they can ask, and those who have no question, they can go on to the next question. Okay. Remember. So then, okay. So I'll wait for 2 minutes for people who have any questions, they can ask. And okay. If nobody has any question, then we'll move on to the next question. Okay. So the next question is throttling. That is the Joule Thomson phase is constant what? So remember we had I think first or second question in which I already mentioned what is throttling. So throttling is an irreversible process which has constant enthalpy, right? H1 is going to remain the H. Let's say for example we have like a valve in here like this. Okay. So here the total enthalpy of mixture is H1, and this is after throttling. So throttling is an isenthalpic process. Okay. That means H1 is going to be H2. The correct answer is option B. Okay. So there is nothing new in this question. So this is so I hope question 5 is clear. And if anybody has any question, they can ask. It is just a conceptual question. Okay. So this is what question number 6 is a bit tricky one. That for real gases, the fugacity coefficient is always what? It is also conceptual based question. Okay. So remember what is fugacity coefficient? Pi F by P, right? And we just remember that ln uh, this one that ln pi is equals to integral z minus 1 by p dp. Okay. P is equal to 0, p is equal to p. So using this expression, you have to tell. So this question I am giving as a homework because it's a very conceptual question. Okay. Okay. So basically, it will depend on z, and because pressure is going to be positive, z, right? And remember, this is what? This is area under the curve, right? So if you plot Z minus 1 by P versus P, whatever graph you will get, it's an area under the curve. Okay. So can area under the curve be negative? Okay. We have to think on all in lines of that. And then if area of the curve cannot be negative, then what this is going to be? Ln of pi is equal to positive, some positive number. Okay. So what is the value of P? Okay, that is what they are asking. Can it be positive? Can it be equal to 1? Can it be less than 1, greater than 1, less than 0? Or it is the other option also I will give it, none of the above. Okay. It can be this also. Remember, so this question I am giving as an homework. So if anybody has any, we can discuss this in the next class. Okay. Very conceptual and very. So I will not be giving answer for this. We'll discuss it in the next class. So anybody would like to try? If he is able to, solve right now, very conceptual question. So anybody has any answer for this? Okay, so I don't hear. So we will move on to the next question and we'll discuss this in the next class. Okay, so we'll move on to the next question. Okay, so let us go. Okay, the new question. So the seventh question. So what is given? The enthalpy expression for binary liquid mixture is this. Okay, the partial molar enthalpy can be expressed as this. The final expression for H1 bar they are asking in terms of X1. So here in this question, everything is given. Like we are given what is HT. This is nothing but H, and its expression is this 400 into X1 plus 600 into X2 plus 400 plus 40 into X1 plus 60 into X2. Okay, and we are given the expression for this H1 bar. We just have to put it. So this is basically instead of a conceptual question, this is nothing but a mathematical question. So basically, what we will do, H1 bar is nothing but H1, which is nothing but this expression. Okay, plus 1 minus X1 multiplied by derivative of this. So remember to put X2 is equals to 1 minus X1. So what you should do first, right? Because the derivative is in terms of X1 and also what the final expression is asked in terms of X1. So you just substitute everything in this expression X2, you just substitute 1 minus X1 and you just simplify it right here only. So you'll get H as some function of X1 only. And when you put that into this expression, it will be very easy to do the derivative and all calculation part. It will be easy and it will straight away give you the answer. So try to do it. I'll give you 5 minutes. Okay. Remember this expression is what we have to use. You have to substitute x2 with 1 minus x1 here and here, simplify it, and then just whatever expression you get, you just put it in here and just take derivative and put this in the expression. You will be getting the answer. Okay. So 5 minutes I'm giving. Anybody has any question? They got the answer? Anybody got the answer? No one? Okay, you want some time. I'll give you, more 5 minutes. So the correct answer is option B. Okay, this one. Try to be very careful with the plus and minus signs. Okay. Anybody got it? So I will start with the explanation. Okay. So what we are given is this, and this is the expression which is given. So what we do is we just put x1 is equal to 1 minus x2. That means, okay, x1 is equal to this and this. Okay. We just take the derivative by putting. So either you can use this method or you can just substitute everything in terms of x1. So how they have done it is, instead of eliminating x2, they are using this expression that x2 minus x1 equal to 1, then taking derivative. This is dx1 plus dx2 equal to 0, and then dx1 is equal to minus of dx2, right? Or dx2 is equal to minus of dx1, and then dx2 by dx1 is nothing but minus 1. So this is also one of the way of doing the things. It depends on the problem and how you have been given, right? Product rule, this is what they have done it, and then they will be replacing it by minus 1 and just simplifying it. So we get it, and then x1 bar is equal to 1 minus s. Okay, you just put in the values, h1 is this which we calculated earlier. Okay, this is, okay, you just put the expression, and then finally you end up with this expression. Okay, it is just mathematics and algebra. Okay, this is the expression. So if you are finding, difficulty in taking derivative, I think it's a good time to just brush up your derivatives by visiting your class 12 notes, and for examination purposes, you should be very thorough and very quick with such kind of questions and with such derivative. So the only way to achieve correct answer is practice. So the more you practice, the better it will be. So just try to, you know, if anybody has any question, they can ask. Otherwise, we'll move on to the next question. So next question is also, as you can see here, conceptual question, enthalpy change of mixing for an ideal gas. That is what they are asking. Enthalpy change of mixing of an ideal gas. Okay, of mixing is what? It is just a conceptual question. This is a very standard, result which we have. This should be at the tip of your tongue. And this is going to be 0. Okay. Yes. So anybody has any question on this? Question 7 or question 8? Very simple questions. It's going to be 0. So how it is going to? So we remember that delta. Remember what is the just try to find what is the expression for delta H of ideal gas mixture. What is this expression? What is the definition of this thing? And once you get the definition, what is it, then you just put the ideal gas equation, that is PV is equals to RT nRT, and then try to find with this expression whatever how you relate with this, and then you'll get it as a 0, right? So the standard results are delta H Ig mixing, this is going to be 0. Similarly, delta Vix Ig of mixing, this is also going to be 0. Whereas delta G and delta S are not going to be 0, right? Mixing Ig mixing not going to be 0. So these are very standard results. I hope you have gone through it. If you have not, you can just go back to your textbook, reference books, and you can just find a derivation there. Okay. So question 8, A is the option. Now we'll move. If anybody has any question, they can ask. Otherwise, we'll move on to the next question. Okay. The next question is also a trivial one. The expression for fugacity. Okay, this they have given, and this is nothing but what the earlier expression ln f by p is equals to integral z minus 1 by p dp. So if you put in the value of z and simplify it, you will get this expression. Okay. Where alpha is going to be okay, and then from PVT data for ideal gas, it is found that this integral. Oh, this integral also they have already given. Now what we have to do, you have just have to find the fugacity of gas. This is very easy question. Ln f by p is what 1 by RT into minus 556.64. Okay, you just put in the values. R has been given 8.314. Temperature is 300 Kelvin. Pressure is 50 bar. You just put in the values, you get. Okay. So I'll give you 2 minutes to solve. Okay. You just check here that ln f by p has been given. Alpha has been given this. RT is this. ln f by p. So this comes out to be ln f by p. Just take exponential on both the sides and multiply it by p. You get this 40 bars. Okay, very straightforward question, formula based question. The answer is option D. Anybody has any question? They can ask. Okay, I'll give you 2 minutes, to understand it. Fairly straightforward question. Anybody has any doubts? They can ask, or if, you can also message also if you have any questions in the chat box. I hope everybody got the solution. Anybody has any questions? Otherwise, we'll move on to the next question. Okay? The next question is also conceptual question. That Levy's under rule applied to each species in an ideal solution at all conditions of what? Pressure, temperature, composition, or all of this. This is also very conceptual question. In order to solve this, you have to remember what is Lewis and rule. It is applicable for what? Ideal gases or ideal liquids or real liquids or real gases, and then or solutions. And then you just a very fairly straightforward question, conceptual question. So anybody would like to try? Answer is this, all of this. Okay. Guys, this is a very conceptual question. I will not, give the reason for this. If you have any difficulty in this question, you can ask, or you can just go back to your textbook and read what is Lewis and rule. So the first statement only it will be there. Definition of Lewis and rule itself it is that. Okay. We'll move on to the next question. If anybody has any question, they can ask, or we'll move on to the next question. Okay. And this is the next question. So I'll give you 2 minutes to solve the question. Okay. Anybody got? This question we have to do match the column. The first is Gibbs-Duhem equation. So which is the Gibbs-Duhem equation? Obviously, this is nothing but definition. It's going to be this. And if you are wondering how you got it, you just, have to go back to the textbook and see the derivation here. It's very fairly straightforward. The definition of Gibbs-Duhem equation itself is this, right? And reversible process. Yes, this is going to be for the reversible process. The second law, first law, sorry. Right? du is equal to, so u here represents the internal energy, TdS minus PdV for a closed system. This is the expression for reversible process for closed system. And for irreversible process, obviously it's going to be this expression. Okay. So the correct answer is 1B, 2A, 3C, which is option B. No, fairly simple. So the reason why I'm including these questions is that with the help of this question, you will be able to, remember your basic. This will also build up the confidence which you have. Right? Fairly easy question, straightforward questions. If you have any questions, you can ask. Otherwise, we'll move on to the next question. The next question is this. Gibbs phase rule is used to define number of which properties? Intensive, extensive, or what? That must be specified to pick. So what is Gibbs phase rule? Okay. Degree of freedom is what? N minus P plus 2, where N stands for number of components, P stands for number of phases, and 2 stands for temperature and pressure for an unreactive system. And degrees of freedom is nothing but number of intensive variables. By definition itself, it is intensive. Degree of freedom is nothing but number of intensive variables which are required to fix the condition of the system, right? So if degree of freedom comes up to be, let's say 2, so somehow we have, if we fix the two intensive properties, the whole system properties get fixed. Okay. Like for example, when degree of freedom comes out to be 2 and you fix the temperature and pressure, so all other properties like volume, entropy, internal energy, etc., they automatically get fixed, right? Any intensive or extensive properties, they automatically, that is what is the definition of degree of freedom. Okay, so option is going to be option A, right? Intensive. Anybody has any question? I hope you don't have any question because this is just a simple definition only. Okay. So now we'll move on to the some conceptual questions and some numerical questions. And then we'll visit the conceptual question. Okay. So we'll move on to this question. We'll start with now this question. Question number this. This is a bit of numerical question. So what is given in the question is determine the fugacity of pure propane. So what we have to find is fugacity of pure propane at this condition at 32 bar and 333 Kelvin. And what are we given? We are given the molar volume of the liquid propane is this. Consider the fugacity coefficient of saturated vapor vapor as 0.91. You may assume Vi does not change with pressure. The Antoine constant for the acetone are given by this. Okay, where saturation pressure is bar and temperature. Saturation pressure is in bar and temperature is in Kelvin. So remember what is Antoine equation? Ln P is equal to A plus minus B by T, I think. Okay, this is the okay. So it is A minus B by T by C. So what is Antoine expression? Ln P sat is equal to A minus B temperature plus C. This is the Antoine equation. No, the correct answer is this one. So I hope question is clear to everyone. I'll give you 5 minutes solve the question. Okay. So remember what we are asked to find. We are finding fugacity of pure component at these conditions of pressure and temperature. And in order to do this, we are given molar volume of liquid, fugacity coefficient of saturated vapor, and Antoine constant. Okay. So try to find the answer. Question is clear to everyone. Anybody has any difficulty in understanding the question, they can ask, and those who have understood the question can solve the problem. We'll give you 5 minutes to solve the question. Anybody got it? How to solve it? So I'll give you 2 minutes. More 2 minutes. The correct answer is option C. Anybody got it? Anybody got it? So I'll start with my explanation. So what we are given, temperature 333 and pressure has been given. Phi sat has been given, volume of pure liquid has been given, and internal constants are given. Okay. So what we'll do, we'll just put the values in internal constant and temperature as this one. Well, we get saturation pressure as this 20.557 bar. Okay, and then we just need to use the Poynting correction factor or the expression for calculating the fugacity of pure vapor. So this is the expression. Okay, this is the expression. Right? Phi sat into P sat multiplied by exponential of VL multiplied by P minus P sat by RT. You just put it in the formula and substitute the values, and you get the fugacity as 19.28 bar. You know, straight away, very easy formula based question. Okay, is this clear to everyone? The answer is this. Fugacity is 19.28 bar. Always remember the units, right? The answer is option C, 19.28 bar. Okay. Anybody has any question? For those who understood, can go on with the next question, and those who have any question, they can ask. Okay. So I'll wait for 2 minutes for any questions. So no questions. So I hope the previous question is clear to everyone. We'll move on to the next question then. So what is given? We are given the van der Waals constant for N-butane and N-octane are given as this, where 1 stands for butane, N-butane, and 2 stands for N-octane. So A1 has been given as this, B1 has been given as this, A2 has been given this one, and B2 has been given this one. And for mixture of these two gases, what are the van der Waals constant? A and B. So what we are given, basically, we are given a binary mixture, right, of 1 and 2, and we are given A11, B11, where A11 is this, B11 is this. Okay, then A22 has been given this one, B22 has been given this one, and what we are asked to find is A12, which will be nothing but equal to A21, and B12 is nothing but equal to B21. So remember, usually the mixing rule which we use for this is Lorentz-Bertrand mixing rules. That is what we call as LB mixing rule. You have to remember the expression for this. Okay, and once you get it, expression for A12 is equal to A21. This is what, as a function of A11 and A12, 11 and A22. Similarly, B12, which is nothing but B21, which is a function of what? B11, B22. Okay. So once, if you know these expressions, LB rule, then you'll be able to find it. So I will just, for those of you who don't know the expression, I will give you the expression. Okay. This is the expression. Okay. This is the expression for A. Okay. So you just put in the values. So we are given A1, A2, and Y has been given as 0.6. And this is the expression which we are using. If you just put in the values and simplify, we will get A as this one, 2.465. Okay. Okay. The correct answer is option C, right? Similar would be the expression for B. Okay. And when you substitute the value, you get this answer, option C. Okay. Anybody has any questions? If nobody has any question, we'll move on to the next question, right? So what is the next question? The next question is this: a binary gas mixture. What we are given is binary gas mixture containing 40 mole percentage, 60 mole percent B. If the fugacity of pure A is this and pure B is this, calculate the fugacity of gaseous mixture. Right? So we are given Ya 0.4, Yb 0.6. Okay, and we are given fugacity of pure A 22.6 bar, fugacity of pure B 33.2 bar, and we are asked to find fugacity of mixture AB, which is nothing but fugacity of mixture BA. Okay, the correct answer is option C, option B. So try to find out the, this is straight away again a formula based question. If you remember what is the relation for this, you have all the information has been given and you just put in the values. So I'll just give you the, for those of you who don't know, how do we calculate it? So this is the expression by which we can calculate the fugacity of mixture, right? So for binary mixture, this is going to be ln f mixture is going to be y1 ln y1 ln f1 by y1 plus y2 ln f2 by y2, right? So this we know, this we know, this also we know, this also we know, this also we know. You just put in the values and remember to take the exponential. This is ln f and we are asked to find f, right? So f is 0.4, y has been given, yb has been given, like this. Lewis fugacity rule, by Lewis fugacity rule you find it, then you put in the values 0.4 22.6 plus 0.6 33.2, you get the final expression as this. Anybody has any questions? I hope the question is clear. If you have any doubt, you can ask now, because the next question is going to be dependent on this only. And for this question we did binary. The next question we are going to give for ternary. Okay, so it's better to concept clear your concept right now. So I'll wait for 2 minutes. If anybody has any question, they can ask, or otherwise those who have understood it can go on to the next question. Okay. So instead of binary, here we have ternary mixture. Okay. So I'll give you 5 minutes. Okay. So anybody has any question in the previous question? So I think everybody is clear, and let us move on to the next question then. So what is a gaseous mixture containing 25% A, 35% B, 40% C on molar basis? Okay, this has been given. It's a ternary mixture, and if fugacity coefficient of A, B, and C are this, we are asked to find what is the fugacity of the mixture. Okay, at these conditions. Okay, so the question is similar to the previous question. I'll give you, 5 minutes of time to solve it, and I'll also give, this is the correct answer, option D. Anybody got it? I'll give you 4 minutes more, 4 5 minutes. Anybody got it? Okay, we'll go on to the solving. Okay, so what is given is, we are given the mole fraction. A is 25%, B is 35%, and C is 40%. And what we are, and pure fugacity coefficient of pure, it has been given. So remember, fugacity coefficient is nothing F by Yi. Sorry, fugacity coefficient has been given 0.5, 0.8, 0.9, and what we are asked, what is the fugacity of mixture? So this is the expression for that. Ln of fugacity of mixture is nothing but summation ln Fy by Yi, same as previous, which one simplifies to becomes this. And when you substitute the values, okay, you get this. Okay, so it will be nothing but, if you know y1 ln of f1 by y1 plus y2 ln of f2 by y2 plus y3 ln of f3 by y3. Expression has been given, each value has been given, you just put in the values using these expressions, eliminate the unknowns, and you'll be able to get the final value as this. Okay, anybody has any question is on this question? I'll wait for 5 minutes. Nobody has any question? If question is clear to everyone, then you can note down this question This is the question which I am giving as a homework, and we can discuss it in the next class. Okay, the options also. You know, you can just take a note of this question. So I'll read the question and I'll explain. What we are given, constant of van der Waals equation. So this is the van der Waals equation for N-butane and N-octane, where N-butane is component 1 and N-octane is component 2, are this. For mixture that contains 40% of N-butanes, these are. For mixture it has been given, for mixture this has been given, that A mixture is this, B mixture is this, and the molar volume of the mixture is this. And what we are asked to find is the fugacity of N-butane at these conditions of temperature and pressure. Okay, so this is the homework question. So the concept we have used in this class only. If you look at carefully the questions we have solved, the concept you will find there only. Okay, we are asked to find fugacity, and these are the 4 options. I'll also give the correct answer. This is the 3.6 bar is the correct answer. Now this is a homework question which I am giving. We can discuss it in the next class. Okay, you can just write it down. I'll give 5 minutes for you to write down. Okay. We will discuss this question in the next class. Okay. You can just write down. Everybody, I think, understood this question, right? Is have you wrote down the question? Okay, I will give more 5 minutes. You can just note down the question and we'll discuss it in the next class. If you like to try right now, also you can try. Okay, so I will give you more 5 minutes so that you can try, because we have time on our hand. So I'll give you more 5 minutes. No, if anybody would like to try, they can try and tell if they get this answer. Okay, I'll give you 5 minutes, right? It's 7:35. We'll give till 7:40. Anybody got it? Remember? So I'll give you an. So this expression has been given, and we are asked to find the fugacity. So remember, and then f by p, this expression is equal to integral p is equal to 0, p is equal to p, z minus 1 by p dp, right? Where z you can find from here. Okay. I've given you a hint. This I hope you will be able to find it. I hope the question is clear to everyone. If you have any doubt, you can ask. Anybody got it? Okay. I hope you have noted down the question. We'll discuss it in the next class. Okay. For the time being, we'll move on to the next question. Okay. Okay. So this is the next. So we have covered this. So yes. And we on to more conceptual question. So what this question is, how many? Okay. Let me first do like this. Yes. So how many phases are present in a single component system having degree of freedom as 1? Okay. So remember, degree of freedom is n minus p plus 2, where n is the number of phases, and so n is the number of component and p is the number of phases. So we are given single component, okay, and degree of freedom has been given 1. So what will be the value of p? Straight away, this is a very straight away question. No, what we are given, degree of freedom as 1, single component minus p plus 2, right? P is equals to 1 plus 2 minus 1. This cancels out. That means 2. That means number of phases is 2. That is what they are asking. How many phases? The option is option 2B. Anybody has any question? I hope the question and explanation is clear to everyone. Okay. And case phase will be C minus pi by 2. Here C represents n minus p plus 2. F is the number of intensive variables. C is the number of components. Pi is the number of phases. Right. This is 1 is equal to 1 minus pi plus 2 phase. Pi means 2. Okay. So for those who are done with this question, we can move on to the next question. And if anybody has any doubt in this question, they can ask. Others can move on to the next question. So the next question is, which of the following statement is true? So the work obtained in an irreversible process is always less than that obtained in a reversible process. A closed system does not exchange matter with matter and energy, and work is a state function, and all of the above. Okay. Clearly, Closed system does not exchange matter, but it can exchange energy. So this is a wrong statement. Work is a state. Work is not a state function. Work is a path function, right? As to this, clearly this option can also not be true. Correct answer is option A. Work obtained in an irreversible process is always less than. Okay. So remember here it is a work obtained. That means work done by the system. So work done by the system is what? Work of expansion or work of compression, right? Work of expansion, right? So if you consider this and this, so it's a PV diagram, let's say. So if you want to connect, let's say this is point 1, this is point 2. So let the reversible process be like this. Okay. Okay. Right. Wait. It will be like this, right? This is point 1. This is point 2. Sorry, like this. If you consider like this, point 1, point 2. So irreversible work will be like this. Area under this one. This one. And we change. Reversible work will be like this, right? Area under this one, right? So blue area is greater than red area, and blue area represents the work done by reversible process, right? So clearly, work obtained in irreversible process, which is the red one, is always less than work obtained in reversible process. Right? That's why answer is option A. Either you can go like this, or you can just start eliminating the other options until you are left with only one option. So I hope the question and explanation is clear to everyone. If anybody has any question, they can ask now. And those who understood the question can move on to the next question. Right? So this is okay. So this is the next question. But I'll give you 2 minutes. If you have any questions on this, doubts in this question, you can ask. Then we'll move on to the next question. Anybody has any doubts? Correct answer is option. Anybody has any question? So I hope this is clear to everyone. We'll then move on to the next question. Okay. Okay. The chemical potential for ideal gas is this is clearly the Lewis-Figure rule. Very straightforward answer. Answer is option C. Mu minus mu naught is equals to RT minus P by P naught. So how you can represent it? How you can remember is it's always chemical potential is always relative. That means there has to be some reference value. So this is the reference value. So it is always a change. So it is always going to be minus mu minus. So anyways, this is not the correct option. So out of this thing, if this is also at some pressure, this is also some reference value, right? And this is going to be positive. Yes. Hence option C is correct, right? Straight away Lewis-Figure rule. So here you can match the unit. So it will not match the unit. It will match the unit. Okay. So there are many ways of approaching this thing. The best way is the if you know it. This is nothing but Lewis fugacity rule, right? Mu minus mu naught equal to RTL and P by P. Okay, straight away question. Anybody has any question? If you are otherwise, if you don't have any questions, we'll move on to the next question. So this is the next question, right? For a component I, the mixture of ideal gases, the fugacity is equal to clearly is partial pressure, right? You don't even have to like why? Because we know for ideal gas, fugacity equal to pressure, right? This is for pure component. Okay, this is for pure component. Pressure of ideal gas, right? But when you have mixture of ideal gases, right? So in that case, the pressure of each component is nothing but its partial pressure. So in that case, the pressure has been replaced by partial pressure, right? But as it is an ideal gas, it has to be like this, right? Hence, this is also conceptual question. Fugacity is equal to partial pressure, right? Option D. Anybody has any question? They can ask. Otherwise, those who have solved it can move on to the next question. Okay, so this is the next question. So this is the question. Similar question I have given solved in the last class also. So just to revise it, I am giving this question. You know, you can what is given? Alpha P, coefficient of volume expansion. It is also called as beta at this temperature and pressure has been given, and coefficient of compressibility KT, isothermal compressibility has been given. And if it is heated at this temperature, from this temperature to this temperature, in a constant volume safety, what we are asked, what is the pressure? And the expression has been given. Okay. So as this is already solved example in the previous class, I expect that we'll be able to solve it. So I'll give for 3-4 minutes and then I'll explain. Yeah. Anybody has any question in this? Any doubt? Everybody understood the question, right? I hope you understood the question. I'm hearing no doubts. For assume that question is clear, and I'll give you some time to solve it. You can also refer your previous class notes, previous lectures notes. From there you can get. So I always believe the certain level of repetition does not harm anybody. The more we repeat, the accurate we become. It also helps in memorizing. Then you don't have to mug up the things. You'll automatically revise everything. Anybody was able to solve it? I'll give you some time. You can take 5 minutes to solve the question, and then I'll show the solution. Okay, anybody was able to solve it? So the correct answer is option C, right? So you can refer to my previous notes also to solve it. Let me start explanation. Anybody got the answer? Okay, so what is given is isothermal compressibility, its value is also given, its expression is also given, and by product rule, what we can do, dou P dou Tv is nothing but, because that is what we need to find, how pressure is varying with respect to temperature, right, at constant volume, is payment constant volume, and what pressure would be developed. So we just use the product rule. So what is the product rule? So any question state, we have this. It is a thermodynamic identity that dou P dou V at constant temperature multiplied by dou V dou T at constant pressure multiplied by dou T dou P at constant V is equal to -1, right? So you just rearrange this expression, you take this here and you multiply everything by -1, you'll get this. So then by definition we have this isothermal compressibility is this expression has been given, and KT has also been given. You just what we do basically rearrange, and we get the expression of this dou P dou Tv is nothing but alpha P by KT, that is the ratio of compressibilities, and its value has been given. Once you take the value, you get this expression. Answer is this. This is very similar, only the is very similar, only the numerical values and the way question has been asked as I have changed it. Otherwise, the whole problem is similar to last the question which the problem which I have told in the last class. Right? In that class, we have solved two similar such problems, and here also one. So I hope you are able to understand the question. If you have any questions, you can ask. If you have any doubts, once we get this thing, we get the gradient. You know, we get the gradient, and then we just integrate this expression, and we get delta P is equal to this multiplied by delta T. Delta T has been given to us, so we get delta P as this 71.42. Okay. So if anybody has any question, they can ask now. Anybody has any doubt, they can ask, or those who don't have any doubt, they can go on to the next question. Okay. So anybody has any doubt, you can ask doubt in any question which we have discussed, till far, so far. Any question, if you have any doubt, you can ask now, or you can even write in the chat box. And those who do not have any question, they can go and solve this question. Now, this is also very straightforward question. Only you have to do the arithmetic operations, the differentiation, and all you have to do. So nobody has any questions. I'll give you 1 minute, some time to think about it. If anybody has any doubts, they can ask. Nobody has any questions. Then we'll move on to the next question. Nobody has any doubt, as I'm not hearing. So we'll move on to the next question. So the next question is the viral coefficient B, the second viral coefficient of a certain gas is given by this expression, where A and B are constant. And using this expression, we are asked to compute what is dou V dou Tp, right? So we have PV by RT is equals to 1 plus P by RT into B, but B we can express as B minus A by T cube, and what we are asked is dou V dou T at constant pressure, right? Anybody got it? I'll give you some time to solve the question. Okay, remember it's just a differentiate. We just have to differentiate this. It all depends on how efficiently you are able to differentiate it. So one way is that you just take V is equals to RT by P into sorry, into 1 plus B by RT, B minus A by T cube. That means V is equals to RT by P plus B by P into P minus A by T cube. Okay, let me just make some space. Okay, that means V is equals to RT by P plus B square by P minus AB by PT cube. Now you just take the differential, dou V dou T P is equals to R by P plus 0 because B and P both are constant, minus A constant, A by B dou by T, here P is also constant, right? Dou by dou T of 1 by T cube. Let me make this room. This is nothing but R by P plus AB by P into 3 into 1 by T to the power 4. This is nothing but R by P plus 3AB by PT cube, PT to the power 4. This is nothing but dou V dou T at constant pressure, right? So this option is correct. Option B is the correct option. Anybody has any question? It is just a differential equation. You just have to take the differential, partial differential. It's fairly straightforward, right? So if right, this is so this question also you can take as a homework. Okay, that what is the change in internal energy at 10 kilomole of gas when it is isothermally expanded from this pressure to corresponding molar volume of this, and the expression has been, the equation of state has been given, and this is also given. And what we are asked is, we are asked to find what is change in internal energy, right? So this is nothing but van der Waals equation of state, right? With A and B values given. So this we can discuss in the next class. Okay, answer is also I am giving. You can try and we can discuss it in the next class if you have any questions. It's a fairly straightforward question. So you can just take the notes, right? So this is the question. Okay. So I hope you have learned so much in this class, in this tutorial problem solving session, and you are enjoying it. And I hope your concepts are getting clear. And if you have any questions from any class till now, you can ask me now, or you can even ask me in the next class. I have also given you today two homework problems, which we will also discuss in the next class. So be sure to try them out. And I'll ask one more time if anybody has any questions. Otherwise, we can close the session. I hope you are able to enjoy it and getting your concept clear. Okay, so I do not see any questions. So I thank you all for attending this tutorial, this problem solving session, and I hope to see you again in the next class. Okay, so I think we can stop now. So thank you all for attending, and I hope to see you in the next class as well. Thank you.